my beautiful KCET aspirants. So welcome back to a new session with KCET Masterstroke series. So here we are going to discuss the PU1 sessions and we are going to discuss today atomic structure. So yes, without further delay, let's get started. First topic is atomic models. So here we are going to discuss the challenges after discovery of subatomic particles, Thomson's model, Rutherford models, atomic mass and atomic number, isobars and isotopes, and limitations of Rutherford's model. So first let's discuss about the Thomson's model. So yeah, there were some challenges after discovering the subatomic particles, that how to adjust those particles in the atom, how they actually looks like, how they are oriented, right? So in order to get a proper structure of the atom, Thomson gave its own model, okay, that almost looks like a plum pudding. So what it says, that positive charge is uniformly distributed in a sphere where the electrons are embedded within it. It's quite similar to that of the, the watermelon. If you cut the watermelon, the red mass of the watermelon is evenly distributed, and the seeds, they are basically representing as electron here, they are embedded within the mass of it, right? So here this is the Thomson model, this is how it looks like. Next, this particular model has some limitations or drawbacks, better to say, that Rutherford further proved. So basically when alpha scattering experiment was done, then it was proved that Thomson's model was not valid. Why? What Rutherford did, Rutherford just set up one radioactive source, okay, from the radioactive source through a small beam, the radiation of the alpha particle was coming out of it and it was hitting the gold foil like that, okay, and the gold foil was further, it was surrounded by a very it calls a fluorescent material, okay, zinc sulfide coated fluorescent material. Means whenever a very heavy particle or radioactive particle, they hit the fluorescent material, we will see the scintillation, we will see the blink of light, okay. So the fluorescent material will be surrounded to the gold foil. So he just started the beam and he can see that the most of the alpha particle was passing through the gold foil, and we can see the beams here, in the several places we can see the blink. But it was also observed that one particle, the trajectory was actually 180 degree back, okay, the path it went to hit the gold foil, in the same path it came back, okay. It was observed that most of the alpha particle, they went through the gold foil without any diffraction. Few of them has been through some diffraction, and 1 out of 20,000 it went and in the same way it came back, okay. It proves that like as most of the alpha particle it went undeflected, it proves that the most of the space inside an atom it is empty, okay. Some alpha particle, there has been through some deviation. It proves that there must be some region that contains some concentrated positive charge, and alpha particle also being positive charge, they gets deviated, okay. Next, one alpha particle out of 20,000 alpha particle, it comes back and the same way it went. Why is it possible? Whenever a very concentrated positive charge as well as heavy, okay, it has considerable mass, then alpha particle, when it goes and when it is getting some overlap with the very high concentrated zone with a mass, it is actually getting bounced back, right? So definitely that positive center is having some considerable amount of mass to bounce back the alpha particle, right? So these are the observation. You can see most of the alpha particle pass through it. It can say that most of the space is empty. Small fraction of they are getting deviation. It it indicates that a positive center is there, that is basically called as nucleus, and that is positive, right? And very few alpha particle, they got bounced back. It means that nucleus, that particular center, it is having some considerable amount of mass, and definitely it's very small compared to that of the whole atom. Okay, let's proceed. Here you can see the positive charge, and most of the mass of an atom is densely concentrated in the very small region, and he named it as nucleus. Okay, and the nucleus is surrounded by the electron that moves around a circular path called orbits. Okay, and the electrons and the nucleus are held together by a strong electrostatic interaction. Okay, let's go ahead. Atomic and mass number. So what is basically the atomic number? Atomic number is basically atomic number of an atom is basically the number of electron, and definitely in a particular atom, in order to maintain the electrical neutrality, the number of electrons should be the number of proton as well. Okay, and if I ask about the mass number is basically equals to the number of proton plus the number of neutrons. Okay, this is basically the mass that is present inside the nucleus. Okay, mass of the proton plus mass of the neutron. Let's go ahead. Isotopes and isobars. Isobars are basically the atoms which have same mass number, okay, but different atomic number. Okay, you can see the example: carbon 614 and nitrogen 714. Okay, for this case mass number is same. Why mass number is same? See, this particular thing 14, this represents the mass number. Mass number is 14 and 6 is basically the atomic number. Okay, so I guess this is clear for you. Okay, for these cases 14, 14, both the cases mass number is same. Okay, next isotopes. Isotopes are the atoms which have identical atomic number but different mass number, means below the number they are similar. Atomic number you can see 6, sorry, carbon 6, both the cases this can be taken as carbon 14. Okay, carbon 12 6 and carbon 14 6, both the cases the atomic number is same. Next, stability of limitation of Rutherford model. So basically Rutherford could not explain the stability of the atom because in accordance to Maxwell's electromagnetic theory, it says whenever any particle, any charged particle, they are in high velocity, they continuously radiate their energy, right? So for the electron also very small charged particle, negatively charged particle. So as a result of this, let's say center I am having nucleus and here the electron is running. So electron will continuously radiate the energy. So once upon a time it will keep radiating the energy and it will follow a spiral path and it will collapse on the nucleus, right? It will follow a spiral trajectory and it will collapse on the nucleus, right? Because once it will run in a velocity, definitely it will radiate energy, right? So here, like if you follow this way, the atom is not stable, right? Next, it says nothing about the distribution of electrons around the nucleus and the energies of those electrons. Okay, these are the limitations. Go ahead, one question: which of the following statement is not correct regarding the cathode ray? Okay, cathode rays originate from the cathode. No, cathode ray does not originate from the cathode. Cathode ray originate from the ionized gas particle that is present in the tube. Okay, next, the charge and mass of the particles constituting the cathode rays depend upon the nature of the gas. Yes, that's going to be true. The charge and mass of the particle of the cathode ray, they depend upon the gas that is present in it. Okay, I guess it is clear to you. Let's proceed. According to the Thomson model of an atom, the mass of the atom, just a minute. Okay, I guess this is clear to you. Let's go ahead. According to the Thomson model of an atom, the mass of the atom is assumed to be, first is uniformly distributed over the atom, randomly distributed over the atom, partially distributed over the atom, none of this. Okay, uniformly distributed through the atom. So let's mark it. Let's go ahead. Rutherford's experiment on the scattering of alpha particle showed for the first time that atom has nucleus. Okay, let's go ahead. Okay, so before going, let me just tell you, please boost up your preparation by enrolling yourself in ABHYAS KCET test series, because it will give you 35 mock tests by which you can, your concept will be crystal clear, and definitely as they are providing completely exam hall like simulation, so you will be prepared for your upcoming KCET examination. Okay, so along with that, it's a bonus that Karnataka batch, Deeksha Karnataka batch is offering for you, that is the KC30 batch. If you need a proper structured plan for your upcoming KCET examination, please enroll yourself in this. Here expert faculties will take the live session. You will get complete syllabus coverage of PU1 and PU2. Test format PYQs also you will get. The batch is going to be started from 21st March. So yes, without further delay, enroll yourself. So yes, let's go ahead with the part 2, that is development leading to Bohr's model. So here you can see we are going to discuss the wave nature of the electron, particle nature, quantized energy level. And in the Bohr's model, we are going to discuss the postulate and the limitation. Okay, so developments, first is dual nature of electromagnetic radiation and atomic spectra. So in dual nature, first we will discuss the wave nature and the particle nature. It means they are saying that electrons are having both wave nature and the particle nature. Okay, and in atomic spectra, we will discuss about the line spectra and emission spectra. Okay, so in particle nature, we will discuss about the black body radiation and photoelectric effect. Wave nature, there are so many in the light also, there are so many wave nature we have seen. Okay, so in particle nature, we will discuss about the black body and photoelectric effect. So this is the dual nature. First, we will discuss about the wave nature, that is the electromagnetic radiation. So when electrically charged particle moves under the acceleration, alternating electrical and magnetic fields are produced. Okay, so here you can see electrical field and magnetic field, they are basically perpendicular to each other. They are called electromagnetic waves. Okay, so light waves, they have this electromagnetic character. Okay, and the energy of that we can explain as E equals to C by lambda. Okay, where C is basically the velocity of light. Okay, let's go ahead. So here comes the wave nature. If the lambda is different, what type of wave you can expect? So if you see the wavelength of the particular electromagnetic radiation falls under the 400 to 750 nanometer, then you can see the light, you can see the color. Okay, so below 400 you will see UV, below to that range you will see X-ray, then gamma rays. After 800 you will see IR, infrared. Okay, then microwave, then radio waves, then long radio waves. Like that, in different wavelength you will see that different electromagnetic radiation is coming out. Let's going ahead. Okay, so an ideal body, here we are going to discuss about the particle nature. First is black body. So an ideal body that emits and absorbs all type of radiation, all frequency. Okay, frequency, like radiations of all frequency uniformly, that is called the black body. Okay, and this emission that is radiated by a black body is called black body radiation. Okay, so now definitely intensities of the radiation of different wavelengths emitted by a hot body, it depends upon its temperature. Like if you just heat a rod, iron rod, first it will be red, right? Then it will be whitish, then it will be bluish. So it depends upon the temperature. So that's what. So the energy that is emitted by the black body should increase dramatically. Okay. In fact, it's suggested that at very short wavelengths, the black body would emit an infinite amount of energy. Okay, so here comes, you can see here comes the nature about like intensity with respect to the temperature. So at a given temperature, intensity of the radiation emitted increases with the increase in wavelength. Okay, so first as you increase the temperature, your wavelength will increase. Okay, as you increase the intensity, I mean, if you increase the temperature, the intensity of the radiation will increase first. Then it reaches the maximum wavelength. Okay, it reaches at the peak. Okay, then the wavelength start to decrease. This is the nature. First it increases, it reaches the maximum point, then it decreases. Okay, at a given wavelength, and then starts decreasing with further increase in wavelength. Okay, so I guess it's clear. As the temperature increases, the maxima of the curve shifts to shorter wavelength. Okay, I guess this is clear to you. Let's go ahead. Okay, so to solve this, Max Planck proposed a new idea. He suggested that energy could be emitted or absorbed in a discrete packets those are called as quanta. Okay, so what is the energy of a quanta? That is equivalent to h into nu. H is the Planck's constant, nu is the frequency. Okay, so this quantized approach, quantized means a fixed amount. Okay, quantized approach explained why energy did not blow up at short wavelengths. Okay, and only certain amounts of energy could be emitted at high frequency. Okay, like definitely that avoids the infinite energy prediction. Okay, so let's go ahead. You have to remember this formula. Next particle nature, that is going to be photoelectric effect. So what is photoelectric effect? If you have a metal surface, on that metal if light or photon particle strikes, then electron will start to emit. Okay, this is photoelectric effect. So the photoelectric effect, you can see h nu equals to h nu 0 plus half mv square. Half mv square is basically the kinetic energy of electron, and h nu 0 is called the work function. Okay, so basically whenever the photon will strike, as soon as the photon is striking, the electron is going out. No, it has to cross the work function, a threshold energy, then it will come out, right? So that threshold energy of electron should be covered, and the electron will come out with a certain amount of kinetic energy. Okay, so let's go ahead. Here we are going to discuss about the development that leads towards a Bohr's model. So here Lyman, Balmer, Paschen, Beckett, Pfund series we will discuss. So what is the concept basically? If you excite an electron, if you excite an electron, it will go from lower excited state to higher excited state. Okay, so once an electron is going from lower excited state to higher excited state, it will absorb energy. But when it will come back to the lower excited state or its own ground state, then it will radiate the energy it absorbed, right? So as you can see, once it is going there in the higher energy, let's say an electron was like the ground state of the electron was N1. Okay, from there it was excited up to N2, then N3, then N4. So while coming back, it will radiate some sort of energy. So the radiation we will get when the electron comes back to the N equals to 1 state, the range of light, the range of electromagnetic radiation that we will get, they are called Lyman series. Okay, we will get in the region of ultraviolet. Okay, after that, if the electron comes back to the N2 from the excited state, then the range of radiation, electromagnetic radiation of different frequency we will get, that is basically Balmer series. Okay, and that falls under the visible range. Okay, next you can see if it comes back to the 3, then it is Paschen series and Pfund and bracket and Pfund, like that it continues. Okay, so the formula that you can use to calculate the frequency is nu bar equals to R is basically Rydberg's constant, that is 109677 centimeter inverse into 1 by n1 square minus 1 by n2 square. Okay, so let's go ahead. So here comes the Bohr's postulate. Okay. Okay, let's go ahead with the Bohr's model. So first postulate is basically, it's all about the stationary state. Okay, so Bohr gave the electron a proper fixed orbit. Okay, means that those are called as stationary state. Okay, so those are basically the integral numbers and known as principal quantum numbers. Okay, 1, 2, 3 like that. Okay, now radius of the stationary state are also given. They are like denoted as Rn equals to A naught of n square. Okay, next energy of the orbit also is fixed, En equals to minus of Rh by 1 by n square. Next, if I proceed further, then for the hydrogen like species, Rn is basically this A naught value is 52.9. Okay, then for higher species you can just proceed with the number of n, you can just change, means which state the electron is, which orbit the electron is belonging. You can put the value of n here and divided by z is the atomic number. Okay, next electrons absorbs and emit a fixed amount of radiation to jump up or down the energy levels, means whenever electron is in the ground state, so to go to the excited state it will absorb some sort of radiation and it will go to the excited state, and while coming back to the ground state it will radiate the energy it absorbed. Okay. One more thing that needs to be told here, that the stationary state while rotating, like the electron in which orbit it will rotate. So for those cases electron will rotate in those orbit only. For those cases the angular momentum, the orbital angular momentum should be equals to n times of h by 2 pi. So from there one more formula, that is mvr. Mvr is basically is the orbital angular momentum. It should be n times of h by 2 pi. Okay, so this is another formula in this where the angular momentum value will be n times of h by 2 pi. Only in those orbit the electron will rotate. Okay, I guess it's clear. Now limitation it fails, definitely it fails to explain the finer details, means if those hydrogen spectra that we are getting, basically if those particular radiation that we are getting when the electron is coming back, if they are kept in electrical and magnetic field, this splits further. Okay, in the electrical field if they splits it is called Stark effect, and if magnetic field they splits it's called Zeeman effect. So it could not it could not target or it could not explain the Zeeman effect and Stark effect. Now splitting of lines in magnetic and electrical field, that's what I told you. Now ability of atoms to form the molecules by chemical bond, that also could not be explained by Bohr's model. Let's proceed. Okay, one problem. With regard to photoelectric effect, identify the correct statement among the following. Okay, number of electrons ejected increases with increase in frequency of the incident light. Okay, no, that's not gonna be correct one. Rather, it's going to related to the intensity of the light. Next point is number of electrons ejected increases with the increase in work function. No. Next, number of electrons ejected increases with the increase in intensity of the incident light. So option C is going to be the correct one. So now we are going towards the quantum model. Okay, so in quantum model what we are going to discuss, first dual behavior, Heisenberg's uncertainty principle, then quantum model. We will discuss the postulate, nodes, quantum numbers, energy of the orbitals, rules to fill up the electron, and electronic configuration. Okay, first let's discuss the dual nature of the particle. Okay, de Broglie's wave particle duality. So they are saying that that particular electron, they are having both wave and particle nature. Okay, or any electromagnetic radiation, they have both the nature. Okay, so lambda equals to h by p. Okay, so Heisenberg's uncertainty principle, it is saying that simultaneously it's not possible to find out the exact position and the momentum of the electron. Okay, so this is the formula, delta x into delta px is greater than equals to h by 4 pi. This formula is important. The significance of the Heisenberg's uncertainty principle is a lot, but for your level, just remember this: it rules out the existence of definite part of the trajectory of the electrons. Okay, from here only the probability of finding electron, this particular concept will arise. Okay, so let's proceed. Conclusion: it means that the precise statement of the position and momentum of electron have to be replaced by statement of probability. That's what I told you, probability of finding electron, that the electron has given a position and momentum. This is what happens in the quantum mechanical model of an atom. So there I will not give a particular electron a particular path, rather I will tell you these particular zone the electron can be found. Okay, so the probability of finding electron is maximum in this particular zone. So I can give you a particular zone. Okay, it's not a path, it's a 3D concept now, it's not a 2D path. Let's go ahead. Reason why Bohr model failed. First, in Bohr model you can see the electron is regarded as a charged particle moving in well-defined circular orbit about the nucleus. The wave character of the electron is not considered here. Okay, next, further, an orbit is a clearly defined path, and this path can completely be defined only if both position and velocity of the electrons are known, but Heisenberg says it's not possible to know that, right? So here also Bohr's model failed. Okay, next, quantum mechanical model, we will go through the statement one by one. First is the wave nature is considered here. The wave nature of the electron majorly considered here. So here comes a new scientist, that is Schrödinger's wave equation. Schrödinger. Okay. So these particular scientists gave the equation that is solved for the hydrogen atom. Okay. H psi equals to E psi. Okay. So these the solution, it gives the possible energy levels of electron that can occupy and corresponding wave function of the electron with each energy level. Okay, now the question is, what is wave function? So wave function is something like, you know, the way we have our own identity card that tells us, that tells everything about us. So wave function is something like an identity card or identity proof for the electron. It tells everything, the whereabouts about the electron. Okay, so now you can see these quantized energy states and corresponding wave functions are characterized by a sets of quantum numbers. Okay, so we will discuss about the principal quantum number, that is N, azimuthal quantum number, that is L, magnetic quantum number, that is M. Another one quantum number is also there, but that was not explained by Schrödinger. Okay, so this definitely it came up as a natural consequence in the solution of the Schrödinger equation. So when the Schrödinger equation was solved, by default these three different type of quantum number arises. Okay, so next you can see okay, so whenever you are discussing about an electron at a particular energy state, then the wave function that I already told you, it actually contains all the information about the electron. Okay, now such wave function of hydrogen or hydrogen-like species, okay, they are called atomic orbitals. Till Bohr's concept it was orbits, now it is orbitals. Okay, so now those wave function that pertaining to one electron species, this is called one electron system. Okay, and the probability of finding electron at a point, it can be given as psi square. Okay, at that particular point. Okay, so probability of finding electron is given by psi square, but psi is the wave function that contains the whole information about an electron at a certain energy level. Okay, so quantum number. Okay, so here we are going to discuss about the, okay, let's discuss about the quantum number at first. So quantum number, if I split, it will come up to be 4 types, right? First is N, that is the principal quantum number. Okay, it gives you, it tells you about the size of the orbital, okay, and the energy. Okay, next comes L, that is azimuthal quantum number. Azimuthal quantum number. Okay, so how L can be defined? L is basically, L exists from 0 to n minus 1. Okay, from 0, the range of L is basically 0 to n minus 1. Okay, now if the value of L is basically 0, it can be 0, it can be 1, 2, 3, like that. It can be 0, 1, 2, 3. Okay, so if the value is 0, it is called as S. If it is 1, then it is called as P. If it is 2, it is called as D. If it is 3, it is called as F. If it is 4, it is called as G, like that. Okay. Next, we can go ahead with the magnetic quantum number. Magnetic quantum number. Magnetic quantum number basically ranges from minus L to plus L. Okay, so let me just give you one example. Let me just tell you, I am having 3p system. Okay, 3p means n value is basically 3. Okay, n value is basically 3. So for n value is 3, I can have 0, 1 and 2. Right, these two orbitals only, right? So I am taking 3p orbital. So p means I am having 1, right? P means my L value is basically 1, right? 3p means L value is 1. Okay, so for this case, m can be minus 1, 0, plus 1. Okay, minus 1, 0, plus 1, minus L to plus L. So that corresponds to 3 different p level, 3 different p orbital. That's it, px, py, pz. For them, the m value is minus 1, 0, plus 1. Like that you can define them. Or else let's take one more example. Let's take 3D. Let's take 3D or let's take 4D. Let's change the principal quantum number. Let's take 4D. 4D. Okay, so n value is going to be 4 certainly, as this is my d orbital. So d orbital means it is, the value is 2. So L value is going to be 2. So m value corresponds to minus 2, minus 1, 0, plus 1, plus 2. So that is the reason if you just assign them, this is my dxy, this is my dyz, this is dxz, this is x square minus y square, this is dz square. Okay, 5 m orbitals you will get out of it. Okay, fine. These are the 3 orbitals, 3 quantum numbers, 3 quantum numbers, and the last one is basically spin quantum number. Okay, spin quantum number, it is having 2 options, either clockwise spin or anti-clockwise spin. If it is clockwise, then plus half. If it is anti-clockwise, then minus half. Okay, so that's the whole quantum number. I guess it's all right. Let's go ahead. So nodes, okay, nodes means where the probability of finding electron is 0. So node can be of 2 types, radial node and angular node. Radial node can be explained by n minus L minus 1 value, and angular node formula is only L. Okay. Next, energy of the orbital. Energy of the orbital basically like how the electron can get filled up. Okay, so n equals to 1 is having the lower energy, then 2, then 3, then 4, then 5, then subsequently this is the way the electron can get filled up. Okay, so rules to fill the electron, here you can see Aufbau principle. In the ground state of the atom, the orbitals are filled in the order of their increasing energy. As I told you, this is the ground state, 1s, after that 2s, then 3s, 2s, then 2p, then 3s, 3p, 3d, like that. This is the energy order. If I just write it here, 1s, 2s, 2p, 3s, 3p, 3d, this is the order. So in accordance to that, the electron will, the energy is increasing, right? In accordance to that, the energy is increasing. So in accordance to that, the electron will get filled up. Next is Pauli's exclusion principle. No 2 electrons in an atom can have the same set of 4 quantum numbers. So we have 4 sets of quantum number, that is n, l, m, s. So for all the electron they will be identical. Okay, next, Hund's rule of maximum multiplicity. Electrons in the orbitals belonging to the same subshell, that does not take place, pairing of electron, one word is missing here, pairing of electrons. Pairing of electrons in the orbitals belonging to the same subshell, it's not possible until each orbital belonging at least one electron. Let me just give you one example. Let's say I am having 3p4 system. Okay, so I can do it like this. Okay, 1, 2, 3, 4. This is the wrong method. What is the correct method then? I have to give everyone single electron at first, then I can pair it up. Okay, so pairing up will take place once all the orbital will be occupied with the single electron. Okay, let's proceed. Electronic configuration, if I just discuss about, then one by one, like any compound we can discuss. Let's say, let me discuss about simple molecule. Let me take calcium. Calcium is basically 20. Okay, so I have to write the energy order at first. 1 is in accordance to the Aufbau principle, 1s, 2s, 2p, 3s. So 1s, S can have maximum 2 electron, P can have maximum 6 electron, D can have 10 electron, F can have 14 electron. Keeping this in mind, 1s2, 2s2, 2p, 6, right? P can have 6 electron, S can have again 2 electron. So how many electron? Total here 10. 3s2, 3p6, then 4s2. That's it. This is calcium 20. Let me just give you another example. Let's take it as copper. Okay, copper is basically 29. Okay, so if I just do it, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, it comes 3d9. But here what happens, you know, this is not the correct configuration. Here everything is same, up to 3p6 it's same. But here it becomes 3d10, 4s1. Why? Because 3d10 gets some extra stability because of being fulfilled. Okay, that's why it exchange one electron with the 4s, so 4s become 1 and 3d becomes 10. So this is one of the not exceptional, just because it wants some extra fulfilled stability, it just takes one electron in 3d10 and becomes more stable. Okay, so this is how you should proceed with the electronic configuration. Let's go ahead. Okay, one problem, consider the following sets of quantum number. Which of the below setting is not permissible arrangement of electron in an atom? Okay, so S value we don't have to check, it can be either plus of or minus of, it can be anything. Okay, so we have to check N, and with respect to N, L and M value we have to check. Okay, so once the N value is 4, for 4, 0 is possible, right? Why? Because L should be N minus 0 to N minus 1. So if N value is equals to 4, the L value should be 0, 1, 2, 3, right? So yes, 0 is one of them, L is correct, and if L is correct, M is also correct, fine. L value is, you know, minus L to plus L, right? So minus L means it is basically 4, minus 4 to plus 4, it's possible, 0 is coming within it. For 5, again 3 is possible and 0 is also okay. Okay, for C, option C you can check, it is 3. For 3, N minus 1 is 2, that is also possible, minus 2 to plus 2, minus 2 is coming among them. Okay, next, this is N3, for N3, L can be 2, okay, but M cannot be minus 3. Let me explain. If N value comes 3, L should be 0, 1, 2, right? L value is 2, right? So M should be minus 2, 0, sorry, minus 2, minus 1, 0, plus 1, plus 2, right? Minus 3 cannot be there. So this is the wrong one. Okay, I guess this is clear to you. Okay, so this is all about the atomic structure chapter. So more numerical you need to practice on the each of the postulates, like not postulates, better to say Heisenberg uncertainty principle, wave particle duality, okay, Rydberg's equation. From there more number of numericals you need to practice, the PYQs you need to practice, that we will come up with the live session. So till then just make sure that your concept is clear about the chapter. If anywhere you find a difficulty, please comment me below. Don't forget to give one thumbs up. If you have not subscribed, then please subscribe our channel and don't forget to share with your friends. Thank you for watching.